So firstly, hello everybody and welcome to today's session. We're really excited to have you here for the first part of a three-part series, our AI Engineering Bootcamp. We're going to be digging into all sorts of different aspects of getting AI in engineering up and running, getting it into pilot phase, into scaling up, and what's coming in the future as well. So today's session is going to be all about kickstarting engineering AI in manufacturing. And actually, I think what we're going to talk about really goes beyond even manufacturing. It's really just equally applicable to kind of any industry. So if you're not in manufacturing, don't immediately run away. Please stay, and you're going to enjoy the presentations today, I think. So first off, I'd love to introduce our panel. We have Armin from Convion, which is part of HD Hyundai's hydrogen business. He's a senior thermofluids expert, and he's going to bring a fascinating customer insight, sort of personal experiences and learnings from having just been through this exact process. So welcome, Armin. Really happy to have you here today and looking forward to what you have to say.
Glad to be here. Thank you.
Awesome. We also have Mike, who is a Principal Product Marketing Manager for Onshape at PTC. Hello, Mike. Welcome. Great to have you here, and you're going to be connecting us to the all-important world of CAD, which is certainly like an essential part of any kind of automation and productivity process with simulation, right?
Yes, absolutely. Thanks for having me, and you know, it's so nice to be part of the panel here. So can't wait to see what Armin has.
Awesome. And then also we have our very own Steve, who leads application engineering and partnerships here at SimScale. Steve, of course, is working with customers on a daily basis. We're doing exactly what we're going to be talking about today. So welcome, Steve. Great to have you here.
Yeah, thanks. Looking forward to the discussions.
Yeah, awesome. Yeah, and then finally, hi, my name's Alex. I'm like a technical marketer at SimScale, and I'll be moderating the session and just kind of kicking off the discussion here at the start. So we'd love this session to be as interactive as possible. So all of the attendees, you've got access to a chat panel and a Q&A panel in your sidebar. Please, treat that as your playground as we go through the session. We'll be keeping an eye on that as we go. We'd love to be able to answer your questions as we move along and keep the discussion flowing. So to get things started, I'm going to briefly share some insights from a survey that we ran over the summer. Some of the audience may have seen this before. So we spoke to 300 engineering leaders, and we were asking them about that. Where are they today with kind of AI adoption, rollout, etc. What progress they've made, what value they're seeing or not seeing, and what kind of learnings and blockers that they've encountered along the way. And what we found was that there's a very broad recognition that AI can deliver significant value in engineering processes, and particularly in simulation processes. So we found that almost everybody recognized that there's productivity gains, and in some cases very high productivity gains to be got from AI. But when we asked actually, what are you seeing today? That's where we saw the kind of the disconnect. So we see only 3% of people, that's like a tenth of the people who recognize the great potential, are actually getting that return on investment and getting that productivity gain. So that's a big difference, and it's very different, of course, to how we see AI maybe impacting other areas of our lives. We also asked about where people are in their adoption journey, and I think that it tells a similar story. We found that the vast majority of people answering the survey either had some AI in production, they were or they were experimenting with pilot projects, or they were just about to start experimenting with pilot projects. But it shows that there's definitely like a gap there between the kind of the expectation and what people are kind of getting today. So interesting interesting numbers, do you think? Armin, I'd love to bring you in here and get your view on how this stacks up against your reality. And I guess just are you in the 3%? That's the question.
yeah, I think so. Yeah, and the different aspects of AI now. Over here, I'm going to be talking about CFD and how, or simulation, and how AI is assisting us in simulation and how we see going forward. But then there are the different aspects of AI in daily work, which I see would be beneficial, and I personally use it. But I also see this spread quite nicely matching our colleagues, different organizations, different companies that I have worked before. It's maybe a little bit too much for some people, and it has some sort of a barrier. But I see a lot of people also trying to use it to their benefit and adding efficiency to their work. And yeah, it's at least to me, it's pretty accurate.
Yeah. Do you think it's hard for people to kind of cut through the noise? I think we all hear like there's a lot of kind of noise. Let's say about what possibilities are. It's hard to kind of understand what that means to you as an individual, as a organization.
Yeah, I would say so. And also maybe different cultures also have different approaches to AI now as well. I come from Finland, and it's maybe a little bit more conservative over here than maybe other countries. But then again, the spread or the distribution, you can see this kind of distribution maybe everywhere. It's maybe difficult for people to trust AI right now, or for some people to trust it. For me, again, it's I would like to make the final decision. I won't trust it myself 100%, but I would use it as a helping to help me get where I want to get. And you will see in my example that in this first example, I didn't trust it either at the beginning. I had to verify it against something else. But then the result was positive.
Yeah, awesome. Yeah, no, looking forward to digging into it. Yeah, and maybe if we indulge a survey for one more stat, we also asked about kind of blockers. What's actually holding people back from getting things moving here? And we saw, so what we found was the top one was data. And I know, Steve, like this is something that I think it was probably the first thing you said to me when we were talking about customers wanting to get started with AI. Data is a big challenge.
Yeah, exactly. I think it's always the biggest challenge when it comes to AI, because there is no AI solution without data in the background to train on, also to validate against. Like you said, Armin, you can't just blindly trust something that you get out of an AI algorithm. It's got to be trained on meaningful data in the first hand. You've got to have meaningful test data to validate it against during the process as well. So it's definitely something I see a lot in our customer base. The data is something that has to come first, and a lot of people are always questioning whether they have enough data or whether they have a well-organized enough data source to be able to leverage AI. And I think that's one of the things that's going to be really interesting to look at today, is exactly how Armin and Convion have gone through this process of generating the data, managing it, and leveraging AI.
Yeah, absolutely. Yeah, and the other one that's kind of bolded there on the slide is the kind of desktop CE tools slow us down. I guess this is possibly closely connected with the data point as well. That the data may be, in like even in cupboards or in different places in a company. but also that those tools might just not have the kind of interoperability that you need. I guess this is one that you must encounter, Mike, as you're also like a cloud-based solution. Is that one of the reasons why you see people moving to the cloud?
Yeah, absolutely. The cloud is a great way to, I mean, having information, in the cloud is the central way any of these AI kind of businesses, that utilize information, you need to have a centralized place to put it. It's usually the cloud. People are coming to Onshape, because they see those trends, and we've been trying to take pragmatic approaches, with AI in Onshape as well, and putting in things that are helpful, as time goes by. So we're seeing that. People are asking us all the time about how they can utilize Onshape and other applications that are related to design and engineering with AI for sure. Yeah, we're seeing that a lot.
Awesome, great. Yeah. So I think, yeah, without further ado, let's get into it. I think I have one more slide here. I was just going to briefly, just kind of outline the shape of the rest of the session. So we're going to hear first about the case study from Armin, experiences and learnings from having been through pilot projects and rollout at Convion, and then Mike and Steve are going to dig into like some of the technology that supports the use case that we will have just seen. And then we'll come back at the end for kind of further discussion and see what kind of questions the audience have come up with. So yeah, let's get started. I know, Armin, you're going to share your screen, aren't you? So I will stop mine and switch over.
Okay.
Okay.
Okay. Just trying to find the right window now.
Yeah.
Okay, I did.
Yeah, that's good.
Okay. Yes. And, okay. Yes. So I will be talking about the optimization task that we had, and the timing. I mean, we had this this task, and then SimScale approached me for this pilot of using the AI tool for the optimization task. And well, we talked about this before, and the timing was perfect. So I gladly accepted that and used it for optimization. I would talk a little bit about the background, the introduction and motivation, and then a little bit about the methodology. That yeah, what do we need from the CFD? What do we need from the CAD, AI, and optimizations? A little bit about the results, what we managed to achieve with it, how we verified it as well, and then also I'll show you a quick demo of how we compared the results, the AI results and the CFD results, and how does the GUI basically look like. Now, a little bit background from myself. I'm leading the thermal filters and simulations team at Convion. We are a solid oxide cell system provider. We provide solid oxide fuel cell and electrolyzer systems, and we are part of the HD Hyundai group, or yeah, HD hydrogen basically. I've been working as a CFD expert now for the past 13 years, both 3D CFD and 1D CFD, 1D being more like system simulation. And the first time that I used optimization was in 2018, and we had a component that we wanted to optimize against an objective, of course. And well, that simulation was quite big. Every time that we simulated, it took hours, and then for an optimization, you need these hundreds, cycles all depending on how many parameters you have, of course. But then in that case, I generated more than like 1,000 points of 1,000 simulation results, and we got some sort of an optimized solution. But then we thought that we could go a little bit further over here. We could use this 1,000 points to create a surface fit, to somehow do a regression over these points, and then design explore the design space a little bit more, and do further analysis and find correlations between different parameters and the objectives that we were looking for. So with those points, we did a surface fit, and we used that fit basically, which would be our AI model, to do further optimizations, now this time much faster. And another case that I had was in 2020, which we used a neural network basically it was system simulation data that we used, that we generated, and then we fitted the neural network. We created a neural network based on that, and then used that neural network as a digital twin to support predictive analysis, condition-based monitoring, and system monitoring, etc. That one was also successful. So I had a little bit of background using AI as a tool that could expand our physics analysis and not only focus on CFD cases. Well, of course, at the beginning, you always need the CFD and the physics model, but then you can build upon that. Now, in this case, we were talking about ejectors. Ejector is basically is operated on the Venturi principle, where you have a high pressure flow from one side, and then you drop the pressure, and through that pressure drop through a nozzle, basically, you create a high-speed flow regime, which can suck in some other flow that you would like to get them sucked in. So it works as a pump, but it's different than a pump. As you can see, it's much simpler, but then it only operates at a certain operating point. It's not adaptable as a pump is. But then inside the ejector, you have all of these different parameters, and since the flow is it's high-speed flow, it's difficult also to capture the flow in CFD mode or even test it. Both of them would be extremely difficult. You have this graph over here, or image over here, which shows some of the parameters that you can use, and any of these parameters, the diameters, the angles, the lengths, they will have a huge impact on your design. So the design is very sensitive to all of these parameters, and getting them right for your application, for your process, could be very important. It would make or break it, basically. Now inside, again, when you talk about the ejector, there are parameters that are of interest to us. For instance, the entrainment ratio, the compression ratio, efficiency. Entrainment ratio is maybe one of the most important, where you want to see how much of the flow you're sucking in, as opposed to the primary flow that you're feeding it. So these are the objectives, basically. They work against each other. So it becomes easily a multi-objective problem, which would be a difficult problem to solve. One other thing that I can add over here is the size of the unit, and that is also quite important to us. Usually in our units or industrial units, you want to optimize the size to your design, and you want to have a specific size that you have in mind. Again, why do we do the optimization? As I said, the parameters are the ejector is very sensitive to all the parameters, the cost functions that I described. We want to reduce the cost. We want to have a wide operating range for different processes. Maybe we have size constraint, and also the cost of all of this is the pressure that you provide at the beginning to the primary flow, and you want to save on that. You can do traditional try and error or parametric sweeps on this, but with that many parameters that you have and that many objectives which are contradicting, and as a multi-objective problem, it will take a lot, and you can never find the whole, it would take a lot to find the whole design space. So the best way is to having an optimization approach to this problem. Now, to have the optimization, you could brute force the optimization with the CFD driven optimization, meaning that an optimization algorithm like the genetic algorithm that we're using over here would be driving the CFD model and doing CFD simulations on each of the generations. That is okay, but then every time that you're doing the simulation, it costs you a lot now. Costs you in terms of time, you, I mean the user, time, and also costs you the core hours. Now, if you have your own system, it would be electricity bill, or if you have a cloud system, it would be your cloud core hours. There is this other way that SimScale has now given us the tools for, and it's AI based optimization, where you, for once, you run CFD models to generate training material, training data for the AI model, and then you use that AI model for your optimizations. And the good thing about it is that you do this CFD data generation only once, and then you can use your AI model for in that space that you have trained it, and you can then use your AI model as much as you want, and rather than waiting for days or weeks to get designs, you basically under an hour you would get results. Now, for that also we need tools. We need to generate that data efficiently, and we need to trust that generated data, which then the CFD code comes into play, where you need to, for instance, in our example, you need to be able to model a compressible flow. You need to be able to model a high-speed regime, and well, in many cases you might need to have heat transfer as well, which SimScale offers us that quite nicely. It's very efficient how the code solves the problem for us, and I could make the code in a way and simplify it as much as basically every simulation would take me between 1 or 2 core hours, meaning that it's very efficient for me to generate data and get the AI model trained for it. And I use that now to have different or various AI models. Now I use 512 cases, CFD cases, 256, 128 cases, just to be able to compare, because this was the first time I needed to check everything as well, and I wanted to compare different models. Where are the sweet spots over here? How much data do I need to generate to train this model? On top of that, then we need a CAD tool that could be parametric, could work seamlessly with our CFD code, and basically generate the geometries that we want. And over there, Onshape was just a natural selection for us. It was really easy to work with. It was really, I mean, the first time that I used it, it took me a day to create the parametric CAD. It was the first time that I used Onshape. I am familiar with CAD tools, but I'm not the design engineer that I would be very comfortable with CAD tools. But it was quite easy, and because of that, now we are actually using Onshape as well for our simulation tasks. So having Onshape and SimScale, it gave us the CFD code that we needed, and then we generated the results, the data that we needed. And then I will show you how the AI GUI looks like in SimScale, how we train the AI, and then we use the genetic algorithm to drive the simulations with the AI model in getting the or obtaining the optimized component that we need. Now, As for the results, as I said, the multi-objective optimization was conducted. We wanted to increase the efficiency. At the same time, we wanted to reduce the size. And we had this, a goal for the entrainment ratio as well. So it was quite a nice multi-objective study. We used both AI and CFD in this case. So I did one optimization with AI, or multiple optimizations actually with AI, and then I did a couple optimization cycles with CFD as well. And at the end, while the actual results, like the absolute values, might be a little bit different, which we will see a little bit when I show you the demo, but the way that both the optimizations were heading us were the same. So at the end, we ended up with the same geometry from the AI and CFD tool. So it was kind of nice to see that the AI tool is also a little bit maybe conservative, which gives me confidence when I'm doing the optimizations. It means that when I get optimized solution from the AI model, it probably is going to be even better than what the AI predicts. So that's nice. But at the end, we substantially reduced the size, I can say that, and it helped us with our designs going forward, and we improved our efficiencies at the same time as well. Again, one major advancement over here is that now we can rapidly produce results. If our teams come to me and they have changed a boundary condition, if they have changed the constraints on the size, I can do another round of optimization basically under an hour and give them a design in an hour, and that's mind-blowing. Like before, I had times when we were doing ejector studies, like I would spend a couple of months to get a design. So reducing it down now and having this ability now inside the company to say that, yeah, we could do this now quickly. It's quite interesting. So yes, now I can show you how the AI model works. So as you can see over here, I have multiple AI models now, which actually all of them are released, and we can see the differences, how they predict, yeah, based on the geometries. And yeah, as I said, I have the 500 cases. I have different mesh refinements that I had in my CFD cases, and I was trying and trialing the software and see what is really important with the AI model. How should I train it? Where should I put my focus on?
Well, so this was the first time that you've been through the process. Is that right?
Yeah. Yes. But I have one example that I can show. For instance, one of the designs that this solver managed to spit out was this one, and as you can see, there are a lot of simulations that have been carried out, and here we have like a CFD run as well, but we can with this toggle over here, the AI preview, we can see that all of the AI models now are over here as well. You can select the AI model that you want, for instance, this one, and then when you are training, I wanted to show you that, but I couldn't, sorry about that, but when you are trying to train the model, you have to select which scalars are you training for. And the scalars are on the surfaces that you select. So you can select the surface, and then you can try training it. So we have selected some surfaces over here to train our AI model, and now we're getting the prediction for those surfaces. For instance, here we're getting the total pressure. Here we're getting the mass flow, for instance. And yeah, so then you can basically compare it to the actual CFD cases, and when you compare, you see that there's a good comparison. There's a good agreement between the AI model and the CFD case. It's not 100%, but it's quite good, and that enables us to quickly churn out results and you know, get the AI model to do the optimization for us.
I used to use CFD quite a bit years ago in traditional software, and being able to get understandable results that are close to a full CFD run, which takes time. I mean, this is really, to me, here as a CAD person and somebody familiar with CFD, this is quite amazing to get some
it's
really quickly.
Yes, exactly. Yes, exactly. And that's really important. I mean, I will always verify the end results against CFD, against my own knowledge and expertise, and anything that I have, I won't trust it, till the end. But it's the time saving that it brings. As I said, maybe 2 years ago when I was doing this, it would have taken me like 2 months to get that I thought there was an optimized the solution. Maybe it wasn't, but now I'm pretty sure that it's quite good, and I've verified it. Yep.
And so when it comes to, sorry, I was wondering, when it comes to validating if you want to take one of those runs and to validate it, would you simply be firing off that exact same configuration as a simulation run, or would you be going into more depth in your CFD run?
So the same geometry will be there, of course, but then the meshing and where to add the refinements and the nitty-gritties about the CFD would be, of course, different to the AI model doesn't have those. But the geometry would be the exact same geometry.
It's got the spaces where all of those things would go in the same configuration, but you would just have to put it out a bit further and then run it. Yeah. Makes sense. And do you do any kind of exploration of changing settings manually and then looking at the running further inferences if you want to do any kind of manual exploration, or do you find that you kind of rely on the automation more?
Well, we have done those before, so we have an understanding of how different parameters would affect the solutions. And when I'm looking at the results of the AI model, I'm looking for these kind of trends, and I want to get affirmation about those trends. If I see that it's going in the wrong way, then either something is wrong with the training, or something is wrong with how I have defined the script behind all of these. So this has been done as well. While we were doing this, I had to change the script quite a lot of times, and then make sure, both on the CAD side and both on the solver side, that everything is going in the right direction. And sometimes even the optimizer might think that it's doing an optimization, and it gets basically lost in finding a local optima, which the space that it's looking is actually wrong. I, as an expert, can see that it's actually wrong. Then I make a change in the script, and I force it to look somewhere else, or give it a wider view so that they can find the global optima that I'm looking for. So you always need to have an expert over there that knows its stuff, and because this was not done in the first run. Maybe I did 20-30 cases to finalize on the script, and then be able to trust it. As you saw, there was a lot of 6 or 7 cases. Those were the cases that I just had a test run, just to make sure that everything's going in the right direction.
Yeah, of course. Yeah. And Steve, did you have a question? There's also something as well we could look at.
Yeah, just interested from the actual training the model side of things. You're not someone who's got a machine learning or an AI background. So how did you find going through that process of actually creating the model?
it was quite easy to do that, and it was very self-explanatory, I would say, how you well, as I said, I mean, I've been training neural networks and stuff. I don't have a degree in data science, but I know a little bit how these kind of things work. And I would say, again, maybe it's good to have some understanding of how an AI model would work and how these systems would work. But then again, I didn't need to think a lot about it. Things were like very straightforward, and the workflow was very straightforward. And as I said, for me, at the end result matters, and how the prediction matters. And when the predictions are good, then has done a good job, I guess.
I was just saying there were a few questions that came in during your presentation there, Armin. Maybe we could squeeze one of them in before we move on. So one was how many simulations were used for the training? I think we saw that was about 500 in that particular example, but you said that you tried that sizes.
Yes, I wanted to see if increasing the number of samples would increase my AI accuracy. And I think there is, I guess, case by case is different, but in my case, I could find the sweet spot, and it was less than 512, and I didn't need 512 cases.
Nice. And then for the validation, how many simulations did you then run to validate the outcome of the study?
Yeah, so on the AI, when I ran the AI cases, I chose maybe 20 of the cases to run CFD on the same cases, but I ran an optimization cycle only with CFD. So I ran like a 40 generation optimization cycle only with CFD, which was like maybe how many was it? I don't remember now. Maybe 320 CFD cases. So AI optimization versus CFD optimization, we ended up to a very similar design.
Right, yeah. And I guess that's something that you were doing because it was a pilot project, so you were kind of doing it kind of like the existing way and the new way kind of side by side.
Yes.
Armin, what's the process like for, like, you're getting answers, like what do you do? Do you go back to the CAD model and make changes? And what's the optimization process actually like for you?
Yeah, so when I get the actual when I get the component or the dimensions from the optimizer, then I usually take that to a designer and I ask them that, all right, now take a look at this and see from your manufacturing perspective how these dimensions work for you, and then if it's produceable. And then they would
for manufacturability and making sure.
Yeah, exactly. Yeah. And then they would give me a design, which would be as close as possible to that to that CFD/AI result, and then I would run another CFD case in that case on that particular model, just to make sure that everything is right.
And maybe for people who aren't familiar, the CAD is on the cloud, the SimScale, the simulations on the cloud, cloud connection. So it's simple as just being in SimScale and pulling
exactly
the data that you want to pull in from Onshape.
Yeah. And also sometimes I want to make some changes, small changes here and there, and see the effect, and then I use Onshape to make those changes if I want to add a rounding, because there are many things that is out of the optimizer scope as well. So if I want to add a rounding here and there and then make some changes myself, then I can easily do it with Onshape and bring it back to SimScale.
Thank you.
Yes, of course.
Awesome. We have we've got quite a few questions. I don't think we won't be able to get through them all right now. I'm going to do one more. Could the designer now just do the simulations themselves? I think that's one that you kind of already answered a little bit. You were saying that kind of the engineer is not being replaced in the process, but But clearly, this could also be kind of, we saw the model management process when you were in the platform there. You can kind of release a model to a wider team of people. So does that mean that it could be a useful design tool? You could provide a model like this to a team of designers.
Yeah, we could do that, and also the designers themselves. I mean, one of the good things about SimScale is that it's accessibility. It's really easy for anyone to access it, and yeah, so the designers themselves also can run the cases. So we can create models for them, just for them to run. But then again, we go back to that, to what I said before. You need to have the expertise, like in this case would be fluid dynamics expertise, to understand the relations between different phenomena, and then see if everything is going the right direction.
It seems like you're still involving multiple people, which is one of the benefits, I think, of having SimScale, Onshape being cloud-based. I mean, we look at the slideshow we're in. We're in a Google slideshow. It's a big blue share button in the upper right-hand corner. Like this makes it very easy to collaborate and connect with other people in your company, outside your company. And like when I do simulation, I'm not the full end expert on simulation, but when I do simulation, I'm getting my design to a point where I can give it to some, I know I have some confidence in it. And then there's going to be other optimization that can happen when I work with an expert like you, Armin. So it's like, it's really good to have that collaborative, version controlled system on the cloud to accomplish all that.
Yes.
Great. Okay. Shall we move on and take a look at what Steve and Mike we're going to show? I'm aware we have sort of 15 minutes left, but we're sort of already doing the Q&A part a little bit as we go along. So I think that's okay. Let's go to Steve. There we go.
Yes. Yeah. Do you see my screen?
Yeah.
Perfect. Yes. So yeah, just what I'm going to do is touch on SimScale, the technology that enables what Armin has shown, and then Mike will obviously touch on the Onshape technology. So the first thing I want to touch on is just how to train that model. So if we go to the AI model section, the same workflow that we were looking at with Armin, and I go to create a new model, I could create a new valve simulation model here, and then I'm prompted with the next step, which is to add my data. So all I need to do is go to the data source that I want to add, where in this instance I have 82 simulations. I save that data source to my AI project, and then I have a data source against this physics AI model that I can start to leverage. I can control some things with this data, like detecting outliers and adding cutting planes to the data. So the cutting planes will be shown along with the surface prediction when this model runs in the user interface. And then I can actually set up the model here using one or multiple data sets. In this example, I've only selected one, but here it could be multiple data sets, and it could also be an evolving data set. So as I run more CFD analysis in SimScale, I can then add that in here and build up multiple data sets to train on and create multiple versions. The next step is to actually select what I want to output. So I'm interested in the pressure and the velocity nodal outputs on all of my surfaces. And I can also select global outputs as well. So I'd be interested in pressure drop across a valve. So I can select that. And then I have some final model settings to select from. And I'm going to say that I want to train for the confidence score. And then I can fire off this model. So if I hit train new version, this is then going to train on our GPU infrastructure in the cloud, and I'll have a new model available to me that I can then publish out to everyone in the organization once it's available. A simple model like this takes about 45 minutes to train, and then I'll have it accessible. Obviously here, once it's ready, I can review the R-squared scores and the deviation against the true results. So we segregate 10% of the data for the regression analysis during the training. So over every epoch, we're comparing what the model is producing against unseen data that we automatically segregate during that process. So it's very straightforward. Just wanted to go through that training process so that you can see it. And Armin, this is the new UI.
Yes.
You'll be able to access this very soon. So a bit of a sneak preview for you as well.
Thank you.
Okay, perfect. So I'm just going to go through some of the other technology. I did see a couple of questions that came in, which I'll try to answer as well. So SimScale, we help engineering organizations to simulate faster by being able to explore thousands of engineering decisions in seconds. And with physics AI, this is really possible. And how we make this possible is by having this platform running in the cloud, very similar to Onshape. Everything is cloud native, so you don't have to have large computers locally to run the simulations, to database the data. That's all taken care of. As Mike also mentioned, and Armin mentioned, there's great collaboration possibilities. You can collaborate from multiple geographical regions, work on the same projects together without having to transfer large data sets. On the platform, we have physics AI for instant results prediction. That's the technology that Armin has been leveraging. And we also have engineering AI to automate engineering workflows. This is something that we're going to cover more thoroughly throughout the rest of this series of webinars. So please do join the future webinars on engineering AI. SimScale is a simulation platform, includes broad physics capabilities, and it's very scalable. So all of the things here provide a great infrastructure for training and distributing AI models throughout your organization. The underlying technology is something I want to touch on a bit. I saw a couple of questions come in on this. What exactly is the technology that we're using? Well, with physics AI, you can get simulation results in seconds instead of waiting hours. So, this is really going back to what Armin was saying, how an optimization study could take weeks, and that is now brought down to hours of time for Convion by leveraging physics AI. You can generate the training data that you need to easily run DOE studies and map out a design space by parallelizing simulations in SimScale. So also a DOE study that could take weeks to run on desktop hardware can also be run in the space of hours. And there's multiple optimization studies available. You can look at different trade-offs, etc. And the underlying technology that we're using is predominantly graph neural networks at the moment, leveraging Navasto, an Autodesk company, and NVIDIA, Physics Nemo. But we're also soon to announce the introduction of some transformer networks as well, which are fantastic at dealing with transient data sources, as well as being able to predict the bulk fluid properties as well. And our solution is physics agnostic. So anything you can simulate in SimScale, you can run physics AI on it. What does native integration mean with SimScale? Well, both the traditional CFD, FEA, electromagnetics, etc. solvers and physics AI can be used in conjunction with each other in the same projects. So when you come to do a prediction, if your results aren't of a high confidence score, so if you don't see a high confidence score in the data that you're predicting, it's very easy to then just run full PDE solve capability there in the same project. And once you have that data, you can train that back into the physics AI model. So the next time you're in that parameter space, you have data to use, and the physics AI model will predict with a high confidence. Physics AI runs in the same environment, so you can use both side by side. And obviously everything runs through the API as well. So you can do the optimization studies that Armin was doing, where you're pinging the physics AI model to get an inference back without having to have any of the UI open at all. This slide, there's a lot of information here. I'm conscious we don't have too much time, so I'm not going to cover this in great detail. But the traditional approaches to physics AI have quite disjointed data structures. You have to prepare a lot of data work to actually get it in a consistent format to be able to train on it. You need a model training infrastructure, typically with GPUs on site. You have model management. With SimScale, we take care of the whole top to bottom pipeline for physics AI. So as I showed, and as Armin showed, all you need is access to SimScale, and you can train your own physics AI models and publish them out to everybody that needs them. Okay, I'll hand over to Mike.
Great, thank you. So I'll just share my screen there. Thank you. And you're seeing the wrong screen, but that's okay. Okay, there we are. So, everything you saw here today was fully, cloud native, right? Which is really amazing. Here at Onshape, we've been partners with SimScale since day one, and we've been working together, cloud to cloud connection. So you design an Onshape, you simulate with SimScale. So we're really, a really close partner with them, and it is very easy to collaborate and exchange data, via the platform because it is cloud to cloud with full version control. Onshape's the leading cloud-based CAD and data management system out there that eliminates CAD crashes because it's running on the cloud. It's running on an environment that's better. It includes the version control, but the collaboration that we were talking about earlier, being able to edit and work together, you can do that in Onshape and then collaborate with your colleagues, on simulation. For design reviews, we have this thing called the follow mode. If you haven't tried that out, it's essentially looking over the shoulder of another engineer virtually. It's like spinning up a meeting like this, but a lot easier. And all your information that you're talking about, your design reviews, comments, notifications are handled by the Onshape system. There's even task management, so you can assign tasks and reviews, resolve those comments, making sure you're not missing anything, dropping the ball in anything, as well as track metrics, to reveal, opportunities for improvement. There's dashboards showing, how long has Debbie Designer been working on this project, or, why is Ed, not gotten to the drawing aspect of things. Things like that can be revealed and dashboarded out. My favorite part, and what a lot of our customers really appreciate, is the Git style version control that's baked into the system. There's no need to manage files and juggle them around. And especially when you're doing simulation, so many different trials. You're iterating, trying out different things. It's really important to make sure you're working on the right thing, especially if you're investing compute resources and things like that, right? So being able to track and branch, if you look at the illustration here on the screen on the right, you're seeing a version graph of a design showing the entire history of what's happened to that document, design for manufacturability. And then you can merge, these changes in if you want, and continue on and release the product, right? So, built-in PDM for release management, Rev A, Rev B, that's all part of the Onshape infrastructure. So if you want to try Onshape, it's wicked easy. You just go to onshape.com and you sign up for an account. It's that easy. It's just as easy, I think, with SimScale as well. Every time I've needed to create an account, it's very easy and feels very similar. I think, if you're going to be using CAD and, simulation that's cloud-based, having both of them cloud-based, exchange data, it makes a lot of sense. that's really what I wanted to make sure we understood.
Awesome. Thanks very much, Mike. I'm just going to pop up one last slide. Yeah, please do join us again next time. We're going to be going into a lot more detail on the next steps in the process, scaling up, and then also using other aspects like engineering AI, as Steve showed before. And I saw some people asking questions about sort of automating case setup and even suggesting decisions based on simulation results. So we'll be covering all of that good stuff next time. And all that remains to be said is thank you everybody for joining today. It's been really great discussion. And thanks to our panel, to Armin, Mike, and Steve for all of the interesting insights.
Thank you very much
Having us.
Thanks, Alex.
Cheers.
Cheers.
Bye.
Goodbye.